Hi, in this video we're going to talk about solution stoichiometry. Now you'll remember when we talked about stoichiometry, we talked about how we're given information on a certain reactant or product in a problem, so that's what we'll call the starting material, and we always start with that measured quantity of starting material, we convert that to moles of that material, and then we use our mole ratio to figure out how many moles we're going to end up with of whatever material we want to know about. And then we can convert the moles of that material to some sort of measurable quantity. Now, up till now, when we've converted measurable quantities to moles or vice versa, we've always used the molar mass. And that's because we've assumed that the measurable quantities we were using were grams, something we could measure on a balance. But that's not the only thing we can measure very precisely. The other thing we can measure is volume. So now we're going to look at a conversion factor of volume to moles. And so if you think about what contains both moles and volume, it's molarity. So I'm going to start with a random molarity here, 0.85 molar. Don't forget that molar means moles per liter. I'm going to state up front that this is an equivalence. And the equivalence would be 0.85 moles equaling 1 liter. What does this mean? It means that if you take a certain amount of solution that you know contains 0.85 moles, that has to be 1 liter of solution in order to be 0.85 molar. But also, if you measure out exactly 1 liter, that liter of solution must contain 0.85 moles. So this is an equivalence. And so, of course, anytime you have an equivalence, you can use it as a conversion factor. And in fact, you can write two conversion factors from that. And one of them will look very familiar. It's 0.85 moles divided by 1 liter, which is how we probably calculated that we had a 0.85 molar solution. The other way you can write it is the inverse. 1 liter divided by 0.85 moles. Both of these are conversion factors. Both of these are equal to 1. And so when we go back to our stoichiometry flowchart, when we're going from measurable quantities of materials to moles or vice versa, we can either use molarity or molar mass. So now let's amend our stoichiometry steps a little. First, we're going to put in a couple of steps that I think of as setup steps. First of all, if necessary, calculate molar masses or molarities. Second, if you're not given one, write a balanced equation. Third, then you're going to take your molarity or molar mass of whatever thing it is that you have some sort of measurable quantity for in the problem. Calculate moles of that thing. Then you're going to use the mole ratio to convert to moles of what you want to know about. And then finally, you're going to use molarity or molar mass of the thing you want to know about to calculate mils of that thing or grams of that thing. Now you might ask, how do I know if I'm going to calculate mils or grams? Well, the problem will generally tell you. If not, you can sort of infer it from understanding whether you're making a solid or whether you're making a solution. So here's a problem, and basically what we're going to look at is the reaction of silver nitrate with sodium chloride, and that gives us silver chloride, which is a solid that precipitates out of solution. And so let's look at our steps. First, we're going to calculate molar masses or molarities. Now we're given a molarity, but we are asked to calculate the number of grams of silver chloride, so we're going to need the molar mass, which I've calculated to be 143.321. Next up, write a balanced equation, if you don't already have one, which we don't, and I'm just going to put this here. We've actually done one of these problems. I think we did one in class, and I gave you the balanced equation there. Step 3 then is to use the molarity or molar mass of A to calculate moles of A. What is A? It's what we know, and what we know is we have 50 mils of 2.40 molar silver nitrate. So we're going to look for molarity and volume. So we're starting with 50 mils, and I'm going to throw in this conversion factor to convert it to liters, because we always convert it to liters when we're trying to calculate moles from molarity. And then I'm going to put in the molarity. Notice I put it in so that liters are going to cancel out. Next, we're going to use the mole ratio to convert moles of A to moles of B. So all the coefficients in this balanced equation are 1, so this is just a 1-to-1 ratio. So finally, we're going to use either molarity or molar mass to calculate mils or grams. How many grams are formed? It says, so that tells us grams from moles is going to be molar mass. So here we're going to use the molar mass of silver chloride. If you calculate that out, you get 17.2 grams of silver chloride. So that's what we would expect. So what I've done here is I've given you another problem with the same reaction. And so I'm keeping the molar mass of silver chloride and I'm keeping the balanced reaction, so we're just going to skip those steps. But what I want you to notice is that we have two pairs here. We have this volume and this molarity of silver nitrate, and we have this volume and this molarity of sodium chloride. So we have numbers of moles, essentially, because a volume and a molarity gives us a number of moles. We have a number of moles of silver nitrate. We have a number of moles of sodium chloride. So we have that information for both of our reactants. And what that tells us is this is a limiting reactant problem. So what we need to do, as with any limiting reactant problem, is to calculate if we used up all of each reactant, how many grams of silver chloride would be formed, and then we'll pick the smaller amount as what we are expecting. Let's start by using the molarity and volume to calculate the moles for each of these two reactants. So for silver nitrate, and I'm just going to do a quick conversion in my head, we're going to use 0.027 liters of silver nitrate times our molarity, 0.425 moles, over 1 liter, so that our liters will convert away. For sodium chloride, we're starting with 12.5 mils, which is 0.0125 liters of sodium chloride, multiplied by the molarity as a conversion factor, 0.613 moles of sodium chloride, divided by 1 liter of sodium chloride. So now we've done that for both of our reactants. Let's now go on to step 4 and use our mole ratios. Now, once again, everything in this reaction has a coefficient of 1, and so we're going to have 1 mole to 1 mole for both of our reactants. Our last step is to use, in this case, the molar mass, because we're looking for grams of silver chloride. So we're just going to put molar mass of silver chloride in here. We can multiply that out and get 1.64 grams of silver chloride. Do the same for our sodium chloride calculation, and that gives us 1.1 gram of silver chloride. And again, in a limiting reactant problem, we're always looking for the smallest amount, and that's going to be this one. That is how much silver chloride we're going to make. So when it comes to thinking about moles and stoichiometry problems, you can always look for grams and use a molar mass to convert, but you can also use a combination of molarity and volume as a way to figure out how many moles you have of a particular reactant. I hope this was helpful, and I look forward to seeing you again soon.